We're almost there. All right. I need to share the link. So let me put it on Slack, isn't it? Where is my Slack? Okay. So that is our video recording session. And now I think I will clear the screen and start with our main stuff. Last time on Monday, we did a lab on autoencoders. We learned many properties of the autoencoder, the ability to remove noise, the ability to come up with much more efficient compressed representations, the ability also to create, in some sense, a stable representations and so forth. We did all sorts of things. Then we studied the theory of variational autoencoders. We haven't done the lab on that so far, but there we learned that encoders can be generative models, and we can use it once you train it on data. It can be used to generate new synthetic data. Like, for example, if you train it on a lot of faces, you can then train it on, then you can generate new faces from that. And you can give two faces, and you can then ask for a continuum of faces in between. So that's the power of autoencoders and creating that sort of representation of models like that. Today, we are going to get back to the concepts in um, attention and transformer. So last time we finished all the bottleneck methods. We did word embeddings, we did this, that, and we did autoencoders was sort of a digression, but we did it because we hadn't covered it in the fundamentals. Now we get back to NLP and we focus on transformers. We did a week of transformers, so I will expect that you have some recollection of it. I'll go a little bit faster and I'll cover BERT because I don't remember covering BERT.
Hey, Asif, Srinivas here. I
Yeah.
have no idea what transformer. So I know you want to go faster, but just like,
No, I'll make sure you understand.
okay, thank you.
Any other questions? Any other thoughts, guys? So stop me if you don't understand. Then do please stop me. Okay? So, all right, so let's get started. Today's topic is attention, transformers, and in particular BERT. And what can we do with all of these things? It's remarkable, actually, how many things we can achieve. So, to motivate that, I'll bring back the concept of the encoder decoder. That's a very good starting point for these transformers. So, suppose you have words, you have a sentence, the cow jumped over the moon. And let us say what you want to do is translate it into some language. Let's say you want to translate it into a picker language. You can try, I don't know if language, you can try
Spanish.
Spanish. Okay.
I'll
Spanish.
translate.
Okay, good. And then you can tell me the translation. So what happens is that it will be, suppose you have tokens, 1, 2, 3, 4, 5, 6, and then full stop is a, this is the end token, so it's a separated token. So suppose you have 7 tokens. When you translate a sentence into another language, it is not necessary that in the other language it would have exactly the same number of tokens. That is one aspect to remember. Right? Some languages you need a lot of words to describe something, and in some languages maybe they are more efficient representations. You can express the same thought with much fewer words. Then And then vice versa, the first language may be efficient at something, and the second language may be efficient at something else. So that's the variety of human languages or natural languages. There is another aspect that you have to consider. Not only are the number of tokens likely to be different in Spanish, but if I were to convert each of these words into Spanish, so the order won't be 1 prime, 2 prime, 3 prime, 4 prime, 5 prime, 6 prime, 7 prime. Suppose these are translations of the words themselves. Then these will not be literally in the same sequence. For example, the French, at least I know, that they uh, say quite a few things the opposite of us. We would talk of the Eiffel Tower, and if and I don't know French, but if I had to try to say it in French, it would be something like Tower de Eiffel or something like that. Um, so it's the other way around. So the sequencing also matters, the order matters. And so the question therefore is, when you translate from one language to another, it is a given that you can't just look up a dictionary and the translated meaning of the word. Even if you tried that, you would have difficulty, because occasionally what would happen is you would encounter a word which is a homonym. For example, the word apple. It has multiple meanings based on the context that you are in. And okay, just give me a moment, guys. I'll give the background. Okay,
I think
so
in French,
with
the
that,
word for in French, the word for potato is something like earth apple.
earth apple is very interesting, right? So yes, that's a variety of language. So, how do we translate from one language to another? And how do we deal with the fact that some words have multiple meanings? Apple, to the techies, is a laptop, or a company, a tech company that makes technical devices. To the farmer and to most common people, apple is an apple that they would eat. So, and like this, there are many, many words, right? You use the word stick. Is it to stick to something, or is it a noun, a stick in hand? Right? So you cannot literally translate a word into another language. You have to be context aware. And that is a crucial word. Any word that you try to translate, you need to know the context, right? Without knowing the context, you can often end up with a bad um, translations. So let's take a word that has many meanings. Would any one of you like to propose a word?
Stand,
Stand. Let's say stand. What meanings would you associate with stand besides just standing up?
like a music stand that
Yeah, a
holds,
music stand. Yes, that's true. A music stand, let's say.
or I can't stand you.
Yes, that's right. Stand. So the other meaning of stand could be bear, tolerate. Yeah, that's an excellent word. Let's take stand. You realize that we learned about word embeddings. Now you'll often see me use the word classic word embeddings. All those word embeddings were very exciting. Word to vec, skip, using skip grams, using continuous, bag of words, glove, fast text, etc. And they do have their place under the sun. But their main limitation is that they are not context aware. So there is one unique vector to stand, for the word stand. But that's not it. The stand is actually three different words which happen to have the same spelling. Right? Homonyms, I believe that's what they call them. Three separate words that happen to have the same spelling in many ways. And you can think of it like that. So technically, they should have had three different embeddings. Right? So there was an effort to create context aware embeddings. And there were things like Elmo and so forth. I won't go into those that tried to create those. One of the things that we will do in the um, current session is we will see how these things are automatically generated. A context aware embedding of words is automatically generated as a natural learning step in the transformer. So just for those of you who are encountering the word transformer for the first time in natural language processing, transformer is a neural architecture which uses sort of either encoder, decoder, or only encoders or only decoders, but basically it has a lot of what I call attention units. So today I'll start by explaining attention units, but we'll get there. But let us just give you the overview. Hereafter, like quite often, we will use word embeddings that are context aware and that are generated as part of your exercise. So for example, if you're writing a sentiment analysis, a classifier of a sentence, positive, neutral, negative sentiment, and you have a lot of sentences, why not create a custom embedding, learn a custom embedding along the way, right? As part of training the classifier. Are we getting that, guys? That is the goal, and we will do that in this architecture. But this architecture, the transformers that we are going to talk about today, so this is a transformer. So we need some building blocks before we understand transformer. And so we go back to something we talked about, the encoder-decoder architecture. Prior to transformer, these tasks used to be done with RNN and derivatives of RNN, RNN and LSTM, etc. Right? The basic model was this. You take a box. So imagine that this is it. You have two pieces, encoder and a decoder. What you do is you pass the sentence, the cow jumped over the moon, as a sequence of series of, first goes S1, S2, Sn. And at each step, this encoder, what it learns is it might emit something. It might produce, let's say, an output, but typically it doesn't. An RNN can, but you may not. You produce a hidden state, H1, all the way to Hn. And any one of these hidden states becomes, and that is the recurrent. So, you feed it back as an input to the box. So this is the recurrent part of it. Strange. You take the output in some sense, one output, you can have another output, but the hidden state or the that you have, you take it and feed it back into the box. Now you say, why would I do that? And it has a natural explanation. See, suppose I'm telling you, if I very slowly, I say this word, the cow jumped, you realize that in your mind, you are slowly constructing a thought, isn't it? That there is there is a thought of what you have heard, and that thought is accumulative, and it is aware. It also depends on the words that came before it. For example, if the word was the cow stood, right? Now I'm using that word stand. So when you have the word stood or the cat, then you, because the two words, the cow, came before it, you implicitly know what is going on. You have your noun, you have your verb, and now you wouldn't, the cow stood, you wouldn't confuse it with a music stand, and you wouldn't probably confuse it with, may or may not be tolerate, but pretty much not, right? And it is the act of standing that remains as a high probability thing. And the cow stood, therefore, is a thought, it's a coherent thought, right? Now, you say over the moon, as the words keep coming up, what happens? You have a thought vector in your mind, you have a thought in your mind, and that thought becomes richer and richer. Every new word that comes, it modifies the thought. But then the new word has to be interpreted in the context of the previous thought, the accumulated thought so far. the partial thought so far. Am I making sense, guys? I hope I'm saying something very sort of hopefully intuitive. So, guys, I will appreciate it when I ask, are we understanding it? If you guys can unmute yourself and give me feedback. I can't see your faces, so I have no idea whether you're following it or not.
We're following.
Yeah. Okay.
Yes, Asif.
Yeah. Okay. It's easy to understand, right? So that is what is understood by this fact that the thought that has accumulated so far, H1, when the first word comes in, you feed it back. It is your context. And then you use not only the second word, but the thought from the understanding from the first word to understand now the phrase, the collective phrase, the cow, right? Jumped, for example, the cow jumped. Jumped takes its meaning much better when you and the whole sentence, the phrase takes its meaning from all three of these, right? So that is why you feed this back in. And so these are called recurrent neural units. Now the recurrent units can be there in, and we didn't cover the recurrent neural networks so much, but this is pretty much it. At some point I'll do that. They still have the uses, but transformers have come and pretty much dominated the scene. We still often hybridize them with RNNs and so forth. So in all honesty, we need to give a proper session to doing the RNNs and LSTMs, but we'll do that at some point. Uh, now, this thing, you can unroll it to look like this. You can say S1 all the way to Sn is going in. So the way it works is that the first thing you have, let's say, sentence S1 went in. It produced the hidden state. Okay, let me just say trigger. This is how the diagrams are made. This is a trigger point. This is S1 went in. So not the sentence, sorry. The word S1 went in, the word S2 went in, and so the cow, right? And at each stage, you're producing a hidden state. It goes in to the next box. So it is the same box unrolled, but just for logical thinking, you think of it like that. The cow jumped, so forth, and then you continue on. And what you have is, this is your second thought vector, context vector. I often use the word thought vector. It may be a bit uncommon, but it helps me capture the intuition of what is going on. So it jumped over the moon, final word. So what comes at the end of it? This entire thing is actually just one RNN, but we have laid it out. We have unrolled it as though it's many. It is the encoder. Now, at the end of it, we'll have the final thought, which is, I believe, 7 tokens, 7, right? So you will end up with H7, right? Think of it as the final thought. Or more formally, the output context. Right? And of course, because we are doing machine learning, everything here is a vector. Right? Remember that vectors go in, vectors go out. So here, of course, you assume that you have taken the words and somehow, for example, converted them to their word embeddings or done something to vectorize them, or just do TF-IDF of vectorization. I mean, just one hot encoded it, or whatever it is that you want to do. In some sense, you have not, yeah, you have encoded this, not TF-IDF, that's for document. You have somehow converted the words into vectors. Right? For the simplicity's sake, just imagine that you have done it with, let's say you used word embedding or something like that. So these things keep going in and this comes out. Now encoder differs from the standard RNN. One thing, there is standard RNN also produces some output. Here in the encoder part, we ignore the output part. We are only caring about the hidden state that we propagate forward and the next word sticks out. Now, so then what happens here now? Let's look at the decoder part. The decoder, the full decoder is like this. The final thought goes in this. And what it will do is, is it will emit the first, let's say that we are doing translation. It will emit out the first word, right? So since I don't know Spanish, I'll just use the word alpha, right? And then it will just emit it out. It's just a trigger, and there is nothing going in at this moment. And then what happens is this output is fed back into the RNN along with the output state. So when once it emits alpha, it produces a hidden state of the decoder, right? So let me just call it encoder. It will produce the first decoder state of the decoder, and then that will go into the RNN again, as well as this alpha will go back in, and it will produce the next word beta. And this process will continue. This hidden state will get, H2 will get fed in, and this is a beta feeding it, and then a gamma will come out. And let's say that this, at the end of it, the hope is that alpha, beta, gamma, right, delta, epsilon, say, let's say that 5 words are enough in Spanish to represent it. So the Spanish sentence comes out. So the way you represent this is, obviously this is unrolled version. In reality, you're feeding it into the box as it is, right? So in reality, what happens is that initially you trigger, then what happens is that some output comes out, some hidden state comes out, edge, and you feed both of these back in, and it looks funny, right? And then yet another output comes out. I find that very non-intuitive to draw, so I won't draw that. I mean, let's stick to this basic diagram. And so by the time the last of these outputs, last of the words have been produced, at some point this will say stop, full stop, separator or something like that. And so you're done. It will be done. So this is your encoder, decoder architecture. Are we together, guys? Now, when people did this using RNNs, the recurrent neural networks, and the LSTMs and so forth, there used to be one problem though. Right? LSTMs and GREs did better than the vanilla RNNs. They had more ability to remember and forget and all sorts of things. But essentially, the theory is that of a RNN, recurrent. You feed back into the structure. The problem that we faced was that if you have a long sequence, imagine a very long sentence, then this sentence, the final thought vector, H final, it remembers, or it is more aware of the last few words. Last few words dominate. And very early words fade out. So if you think of this final thought vector as sort of, you think of it as a gradient. As color, the early vectors were, let's say, blue, and progressively the later words you paint them red. So what happens is when you look at the final thought vector, ideally its color should be midway between blue and red, right? But what tends to happen is it is more influenced by later words, so it is far more red than it is blue. Are we getting the concept, guys? Huh?
Yes.
It happens to us when we listen to stories as children, isn't it? Suppose there's a very complicated story, and somebody is told, we tend to remember the last part of the story, right? So if you take a 2-year-old and say this happened and he did this and X did Y and then Y and Z then did this, and then you go back and ask the child, let's say that X has done something, X has jumped, and Y has eaten an apple, and Z has done something else. But you ask the child who jumped, because they remember the Z, they're much more likely to just repeat the last name. Right? They'll say Z ate the apple. Right? I don't know if you have observed this with children. I used to observe this. So there is a slight, like I suppose it's a very hand-waving argument, but that's the basic intuition that as you train it, because the final, this vector, it has finite size. You give it a finite memory, right? It's so many bytes of space that you have given. So what tends to happen is ultimately, so it is a vector basically of some dimension. Let's say that it's a vector x final. It belongs to a vector space um, of, let's say, d dimension. So you have d values, the d floating point values here. Those values get much more weight towards recent words because they come and they wash over the, every time a new word comes, it washes over and modifies this into the next hidden state. So that's what goes on. Now, though that is a limitation, it depends upon what era you are in. When the RNNs came out and all of the Celestines Jeru, they were a runaway success. They were absolutely amazing. And people used to talk about the unreasonable effectiveness of RNNs and so forth. So very, very influential articles. And everybody was puzzled that it's working so well. And for short sequences and for many variety of situations, they do work very well, right? You could do time series with it. You could do many, many, many things people started doing with the recurrent neural networks. So they had quite a dominant, sort of quite a dominance for many years. And then people began to be more aware of the limitations the more they used it. And the biggest limitation was exactly this, that given finite memory, it tends to de-emphasize earlier words in the sequence and be much more colored or influenced by later words. That is one limitation. But an even more and limitation, which is not a conceptual limitation, but from a very practical perspective, from an engineering perspective, RNNs practically ignore the massive parallelization that you have in today's AI machines. So today's AI machines are usually stocked with tensor compute units or graphic units, like GPU cards or TPUs, tensor processing units or GPUs. And all of them can do a lot of vector processing. They can do a lot of parallel operations. The problem with this recurrent or this particular way of doing encoder decoder was or is that we have no way to parallelize. You have to feed in the token one by one, right? And so it is a little bit slow process. Uh, there's some optimization you can get for vector processing, but not much. And so you had two worlds. In the world of image processing, there was massive progress because of the use of hardware, optimal utilization of hardware, this parallel compute capabilities. In the world of NLP, though, we didn't quite have the benefit of that. Right? So that was one aspect. Also, transfer learning is not as sort of smooth as it is with transformers. So there's some practical aspects also that come in. But from a conceptual perspective, the sort of the fatal flaw with them, if you use the word, for very long sequences is um, it tends to forget the earlier words or de-emphasize or not remember the earlier words. Right? So then the question is, so let me summarize what we are doing. What we say is that we need something. The architecture of encoder decoder stays though, encoder. So let us say that you feed it a sequence. Let's say that you have a sentence made up of word. Now I'll just write the word W, okay, W1, W2, Wn, right? This sequence goes in. This is your sentence. Obviously, you feed it the word, first word first, and what it finally comes out is people often use H as a hidden thought vector, or they use the word context, right? Encoder context, and sometimes they say this is the encoder context, or whatever, or they'll use the H, like I am using H final, the final hidden state that comes out of this encoder. And then that state goes into the decoder, and the decoder, this is your decoder, Actually, I'll use the word decoder down here because decoder, because this keeps emitting words, right? One by one, it keeps emitting the words, right, in a sequence. So to take it further, decoder, how does the decoder work? It has awareness of the thought vector, the final thought vector. It uses the words that it has produced so far, alpha, beta, as another context that it will use to predict the next word and the next word and the next word, right? So all of that, it uses, and then this is your encoder decoder architecture, as it is called. This is what it is. Now, keeping this idea here, I'll take a small digression. People asked this question that how do we address these limitations, the parallelization aspect, and the fact that the attention doesn't stay with, like you don't have long span sequences handled very well. So then in this, with this as a backdrop, there was a pretty interesting development. There was a development of a concept called attention. This was in 2014, and then subsequently followed with another paper in 2015. Those are the, so you can look it up in the section. Concept of attention, and the concept of attention is actually very simple. It sounds very mysterious, and people get quite often frightened when they look at the architecture drawn and different PowerPoints and so forth. It may look intimidating, but the idea is actually very, very simple, and hopefully we will understand it in a very simple way. So this was in 2014 and 15. And what those researchers did is they took the RNN, which was a dominant architecture at that time, and some variant of it, LSTM, etc. And then they added attention to it. They started adding attention, this concept of attention to that. Now, what it is, I have not explained. And so then they started getting much better results. And they knew that something is up, something very interesting is happening, right? But so results. So the whole question is, what is attention in that thing? So before I do that, I'll peel the onion, or the concept of attention. I will treat it as an onion and peel the layers one by one. Huh? So at a very intuitive level, you can say that, see, if you go back and look, we have many concepts. We have, if you look at the thought vector, we have H final. But before the H final, there was H final -1 all the way to H1. All those thought vectors were there. The earlier thought vectors, or the earlier context vectors, they were very aware of the early words in the sequence, isn't it? By definition, because they haven't seen the later words at all yet. Am I making sense, guys, on this?
Right.
Yeah. So with that, so given that, so why not take, when we are decoding, why just take HF, the final thought vector, or why not feed it in a logical way, or in a sort of a conceptual way, all of these context vectors, and learn which context vectors are more important than others, right? If there's repetitive and so on and so forth. In some sense, in some way, clever way, learn to utilize all those thought vectors, because then there would be in some sense, a democracy of influence. All of the words will find their place under the sun, and they won't get forgotten. The early words in the sequence won't just fade out. Are we making sense?
Yes.
So this was the basic idea. The concept of attention is, can we, while we are decoding, utilize not just the final thought vector, but all the previous thought vectors, right, along with it as a context. And obviously, you have to give certain weightages to them, like which thing to, for this step of the decoding, which one I should give more emphasis to, and so on and so forth. And you can learn those sort of a thing. And that's the technical detail of attention, that I will get into in a little bit, right? So do we understand that, the concept of attention? So now we'll peel the onion further, and we will write the sentence, the cow jumped over the moon, and try to build it up in a slightly different manner. The cow the moon. So see, when you are decoding, you are giving, so suppose you have already generated alpha, beta, gamma, three words in Spanish. So they together form a context. That's one context. You're also feeding in this HI, the different values of HI. So the question is how much importance, etc., you give to them. You can figure that out. You can train it and so on and so forth. You can look at what to seek, right? And you produce the word. And you were doing it with RNN. It was still sort of a very sequential operation, right? You got away, you solved the problem of longer sequence, but you still had this a big problem that the whole thing was not parallelizable. So then came in 2017 December a landmark paper, which is it has become almost like a it's sort of a favorite phrase within the NLP community. Attention is all you need, right? So this paper introduced the transformer, the concept of a transformer, and it claimed that you can actually do everything that you were doing with the RNN or RNN plus attention by throwing away the RNN altogether. That's quite a remarkable thing to say. You're saying, let's throw the RNN out of the window. And RNNs were the dominant thing at the time. So how in the world can you do that? So the first thing is that you can't just push all the words at the same time through this encoder. That would be disaster because the sequence, the ordering of the word matters. So the first thing you need to do is you need to give a positional encoding to each word. In some sense, you have to say that this is the first word, second word, third, fourth, fifth, sixth, right? So if you are going to feed it, you have to feed it as like this sort of a pair, a word and its position encoding, right? And if you can do that, then imagine that you feed it into the box and a box. All of these words at the same time, let's say that there are n words, you feed it all at the same time. And what you do in some sense is you come up with these hidden states that we have to use, right? The H1, H2, etc. that I was thinking, except that the idea is taken a bit further. You say that if we consider each of these words to produce their own value states, um, then how much, like when I am decoding, converting this word into French, right? The first word into French, this is number one and number two. When I'm converting this into Spanish, sorry, then how much should it care about what comes later, right? Or the other words in there. We need to figure that out. So there is a very interesting analogy to this that I like to use. Well, I don't know if it's very interesting, very obvious analogy rather. See, most of you are familiar with SQL databases, a data access, right? So in a data access, what do you have? You have some sort of a primary key, some key, right? K1, Kn. And then you have some values sitting there, a value vector. The rest of the things you can consider to be, like if you treat the rest of the columns together, they make a value. And so what do? You need three things. You need a query, which would be something like select star from table T, table T, where now what happens? Now you have to say a K is equal to, and now you have to give it a value, a query value. Does this SQL sentence look very obvious? And this is what we do. It's a very intuitive thing to do with relational databases, for example. Am I making sense, guys? You can say a K is equal to like, I don't know, if it was a number, I could say K is equal to 15, or K is somebody's name, and I could give the name there. So guys, tell me that this intuition is very obvious, right? This is how we access data. This is data retrieval,
Yes.
right? So now this is an exact and deterministic process. Here, what are the things we have? We have, of course, the key. We have the value. Of course, think of it as the row, the rest of the row, the meaningful part of the row, right? A key is more or less like the coordinates, right? Value is the real deal, real thing, in some sense, isn't it? But at the same time, you also need a query, because if you're going to go and get a particular row, you need to have some query to put here. Query value, query like 15 or something like that. You need to feed that in to your SQL, right? So you need three things. So to do your retrieval, key, value, so database is there. And then you need to do, I mean, you take the key, you take the query to find the best match key, right? Typically, you do a match to key, and then retrieve associated value, associated. Would this be a standard pathway for us to do a data retrieval, right? So we apply the same idea. Now, this is a deterministic thing. Suppose I slightly weaken it. So sometimes you say a K is equal to 15. We can often give it like name, key, where K like. Have you seen this kind of a syntax sometimes? Like PPL, or I don't know, some word, ham. So now it will pick up all sorts of matches, hammer, ham, Hamlet, all of those things will come back from this, isn't it? Are we together, guys? In select query, select star from T where K is like that. Sometimes you give a weak query. You don't know the exact answer, but let us say that you are fairly sure that only one guy will match, but you don't know what it is called, right? You remember only some of the term. So you give a query term that is near the key, not exactly the key, matching the key, but near the key. Those of you who have done a lot of SQL, please tell me that this is very obvious. Anybody? Isn't it? We do that. So now let's take that idea a little bit further and say, suppose, now get into the probabilistic domain. Suppose information was stored, in quotes, stored somewhere by all the words were stored by the key. So every word I had associated with it a key, ki, and a value I. And imagine that this is sort of the storage of the word, right? Then what happens? What you have to do is, suppose you have another word. You want to find out, suppose you have a qj, you want to find out or retrieve a value, a sort of a value. What will happen is that you want to find the similarity between ki, qj, right? If it is not an exact match, in the probabilistic domain, the most crucial thing for retrieval would be something like the similarity, isn't it, guys? Sanjay, are you getting that?
Yep.
Yeah. It's a, so you get the similarity is the best you can do. But if you
This
Mhm.
sorry to interrupt you. Can you please repeat this QJ? I lost it in between.
Okay, I'll repeat that. See, when you do SQL access, Sudhir, is this the path, query to match to a key in the database to retrieving the associated value?
Yeah, I got that. Even I got that WI, for some retrieval, you need KI and VI. So I got that piece.
Right.
What I got lost is, the QJ
Yeah.
and
So look at the sentence. Select something, something from. Right? Maybe I can say select value from, right, from some table T where uh, Ki is equal to some query object, some query value, right? Something like 15 or something like that. Then if I weaken this in databases, you do that using the percentage symbol, like that. So suppose you know that there is a guy, right, whose name starts or has, uh, but you don't know what is the first letter, what is the last couple of letters, but you vaguely remember that this is there in the name. Then what do? You just say ki like, and then you give in quotes some sort of a something like this in your SQL query, right? It is no more equal to, but it is a like, right? So now take that idea from deterministic domain to a probabilistic domain. I'm just trying to give you the intuition here. Take it now to our world of machine learning. Nothing is ever equal to something else exactly in our world, right? So the best we can do is a similarity between a key, ki, and some query that you give. So let me give it a term, qj, some query value that you gave, right? Qj. So the best you can do is look at, when you are searching or retrieving the data, look at the similarity between them, how similar they are. This is the equivalent of your like.
Okay, yeah, I got it
Now you got that, right? So now let's carry, and that is this similarity. Now we will change the wording. You are retrieving. Now think about this. Being in the probabilistic word, what will you end up here? For every word, if you take QJ as a probe, it is often called the query or the probe, just like in the database, you probe the database data. If you apply it, you will end up with all sorts of, and the basic similarities, let's say machine learning was the basic similarity that you can make between two vectors. Dot product it. So there you got that. Simplest similarity between two vectors you want to see, just take their dot product.
Yeah, sure, got it.
So you take the dot product of these two, and there is more to it. But let's say that for all of these, you do a ki, a qj, and then what happens is this gives you, and then associated here are those values, v1, v, ki. So k, this is finally kn. This was k1, right? And this is a vn, right? Suppose there are n words. So you took some particular probe word, and you could do this similarity to this. And now what happens is, suppose you do a dot between these two. So let's imagine that you're doing a dot between the dot product. We haven't gotten to attention, guys. Huh? Don't think of this as the more formal definition, but we are getting very, very close. So now what happens? Suppose I retrieve data and I say that we now do a probabilistic game. We don't just get back one row, but we get many rows, all the rows. But if it is not very similar, we'll just take a pinch of it. If it is very similar, then we'll take a lot of it. If you imagine these things to be data, just think that if the similarity between the probe and the key is weak, maybe a pinch, a little bit of a salt to add to your soup. But if it is huge, if the two vectors are very aligned, very similar, then take heap spoons of that material. Right. So what will you end up with? The value that you will retrieve, you will end up retrieving all of those values, v1, vn, because no value will be left behind, except that each value would be weighted. They'll be weighted by the similarity k1 qj, isn't it? A k to Qj V2. Are you getting it? This gives you how much of it you retrieved, right? This is like that in the same way, and then you will have Kn Qj, whatever the query is, times Vn. So far so good, guys. You'll end up with this entire a vector, which is basically all these things for word one, right? With me so far, guys? Please unmute yourself and give me feedback.
Yes.
If there's anybody who hasn't gotten this intuition, ask me about it. And now comes, observe one thing. What we have done is we have just done a weighted retrieval. Weighted, and in some sense it is like it has the flavor, of weighted averaging, weighted retrieval, like weighted averaging, when you do weighted averaging, except that you're not dividing it with a denominator here. In a weighted average, you would divide it with the sum total of everything. You're not doing that, but it is that. So at this thing, how much of each amount you get, there is a word for it. You are saying that this query attention that the query J gives, the attention vector is this. The amount that it has retrieved, which is a weightage, each of the values weighted by the similarity to the query, is basically your attention vector, K1, Qj. Now, why is it called the attention vector? We will just change our way of thinking about retrieving some amount from the database. Now we'll change it to, we'll just put a small twist on it, Kn Qj times V. So, by the way, this math is not exact. There is some exponentiation, there is some, soft maxing and blah, blah, blah. So ignore that for the time being. So, and there's also a square root D and so on and so forth. So let me just not call it attention. So let me call it almost attention. The word for it is almost A. So almost A vector is like this so far. Right. So now, before we go further into the math, let us ask ourselves this question: what is this? And what is this query term? And therein is the magical thing of the paper. The main idea of the paper is that it is the word self-attention. So if take the sentence and all the words in the sentence and make the words pay attention to all the words in the sentence itself. So in other words, if the query term Qj is a word in the sentence, and let's say that the sentence has 7 words, Qj will have a dot product in this thing with all the 7 values, isn't it? You will have a Q1, Qj, the same thing, right? So here you'll have V7, right? So, but then you ask, no, wait a minute. Won't Qj will have a lot of similarity to itself, to its own key. What you do, and there's a bit of a clever thing you do, not necessarily, you train the system in a very interesting way, such that a word's query probe vector and the key will be very different, because you don't want a word to pay attention to itself, right? So you play with that. What you have just ended up is, and the retrieval of the data is equivalent to saying instead of how much data am I retrieving from the database, the thinking is how much attention is this word J, giving to the words in this sentence, all the words in the sentence. Are we together? So that is the that's sort of the moment you understand this, the rest of the mathematics after that actually begins to fall through very easily. So one of the things that happens is we don't take just, so now let's look at this term, Ki Qj. You know that some some ki will be very close to qj.
Asif, can you repeat the last sentence, last punchline, what you said?
What I said is that, I'm saying that you use the query to get different amounts of values, the values like v1, v2, v3, v4, right? So those different amounts are given by the level of similarity. So it's just weighted retrieval. Now change the thinking. What if the query, so what if what you're retrieving, these values are associated with the words, right? The key is, so each word has a key and a value. So now when you come up with the query vector, obviously, and somehow, you have magically created the keys and the values. Now this probe can go against those words, keys and values, and then create its attention vector effectively, almost attention vector, not the full, right? It can do that. Now you ask this question that, all right, if the words have keys and values, what in the world is this query? Where does this come from? And the interesting thing, the answer to that is, hey, you know what? Whenever a word is searching, is looking at other words. So imagine that you have eyes, right? So with these eyes, you look at other people, isn't it? Think of each word having its own eyes, and those eyes is the query vector. So each word, therefore, has three things built in. Word I will have a query vector, QI. It will have a key vector, a value vector. So key and value vector is obvious, right? If you want to store a word, you'll want to have some key and some value, if you think in terms of information retrieval. But the QI, the fact that every word has a unique probe associated with it, right? And it probes other words in the sentence. That's where I believe the word self-attention comes in. Right? The self-attention. The words are paying attention to each other in the sentence. Right? Now, the amount, so we are talking about how much of a V1 is sort of like the value, how much of that to retrieve from the database. So the shift in thinking is, it is not how much to retrieve, but how much attention to pay. It's not a big shift. If you bring a lot of from the database, let's say that you have many things there. You have rice, and you have I don't know, lentils, and you have sugar, and you have salt. Right, and so a typical dish that you would do is you will pay a lot of attention to rice and a lot of attention to lentils. You'll take scoopfuls of them, bring it, and you will take a rather modest amount of salt. You see that, right? Because, so in other words, you say that your query vector will be much more aligned to rice and lentils to get your soup and food, a main staple, right? And less aligned to salt. You'll fetch less of the salt from the system. Or another way to phrase it is, if you remove this from the system business, because there is no real storage going on, now let's bring it to what we say. What we are saying is that we are paying attention, this query vector, this query of a word is paying different amount of attention to different words, right? Or if you were to think of those words as sitting somewhere, it's fetching to itself different amounts of it in many ways. Do we get that intuition?
Yes, Asif.
Yeah. So that's a crucial intuition, and that explains why you have these three vectors, K, Q, and V are there, and this self-attention thing comes in. It's quite interesting. But now I'll just, if you got this much, guys, the rest of it is just the mechanics of that. So what happens is when you're looking at similarity, so let me use the word Sij, right? So suppose you have lots of similarities, S1, J, S2, J, S, and J for a query J, QJ. Associated with this, you have this. Suppose you have, actually, let me say it's an arrow, right? It's not a dot product. It's a square bracket. Right? So suppose you have these values, that you have similarity of the query to the keys. these are the similarity levels. Quite often, we have been using in machine learning this technique over and over again. We want to emphasize the bigger value. How do we emphasize the bigger value?
Waiting.
Exponent.
We do softmax.
We exponentiate it. We exponentiate ij, right? Ij, right? And then we come up with numbers which are all positive, which has also really amplified the bigger value out of them all. So whosoever is the tall guy, you have made it really tall, right? Given the person, let's say, a 10-foot pole to stand on, right? So the person stands out. But then it's good too, because when we talk about attention, if you think of attention as a pie of size 1, what would you like to do? You want to sort of normalize it, right? So the way to normalize something is, you remember, how do we normalize it? Summation over e to the I j, sum of all values of I, which basically means is, suppose you're looking at the QSIJ, similarity ij, 1, 1, 1, similarity 1 will be, it will be similarity ij, similarity ij. Okay. So the new value, let me just call it the S tilde, is this value, Sij, sorry, similarity exponentiated ij, or in this particular case, 1 and 3, divided by summation of all the similarities. So for example, here you're looking at the probe J. So let's just say that you do S1, 3 plus e to the S2, 3 e to the Sn3. So I won't go into that. We know how to do this summation, right? So you divide it, and what do we call this kind of an entity? When we exponentiate it and normalize it, we call it a
Softmax.
softmax. Exactly.
Softmax.
Softmax, right? That's the purpose of it, right? It sort of takes a bunch of numbers, make the tall guy much taller, and then makes them all positive, and then at the same time, essentially converts them into probability or proportions, if you want to think in terms of that. So softmax is a good thing to do, just generally to amplify the signal. If you are really paying attention to something, just make it stand out that it's paying a lot of attention to it, right? So that's why you do the softmax. And so now you have pretty much gotten to everything. So I will say that the attention, let's say that you bring in a probe J, the attention vector, or the attention it is giving to each of the words is partly this exponentiation, this S tilde of the similarity, the softmax of similarity. So S tilde is approximately softmax of Sij, right? Is basically something like that, similarity softmaxed. So this is literally what it is. It is, so any one term, this is ki, and qj, dot product, right? And then you can do it in matrix notation. You throw in your transpose and so on and so forth. This, and then what do? So let's work out the pieces. No, I'll take a little bit more space here. 1 second, so I can write it in bold. So you softmax what? The similarity, which is the, so this is ki qj, right? I'm using q because the paper uses q. Right? Why confuse? Let's continue to use little q, right? It is the softmax of this, except that they do at times the v. What is this? VI, right? This is the value, how much of the value you retrieve. The only thing that I missed here is that you also divide it by the square root of the dimensionality. D is, let's say that KQ, all these vectors, K, Q, V, they belong to a d-dimensional space, right? in the original paper, it was 64 dimensions, right? So square root of 64 would be 8. So it's just a technicality that it just makes it better, more stable or whatever, to divide it by the square root of d to normalize it a little bit. But other than that, it is nothing but this. So if you look at the attention vector, it is, if you think of attention as how much of a certain value to retrieve, this vector tells you how much of it to retrieve. And that brings you to the very celebrated, perhaps the most celebrated equation at this moment in the field of natural language processing. This is your attention. Are we together?
Asif, how do we know that the value of the, you mentioned that the paper is 64, right? So is that a variable or it's like a constant?
No. See, I can imagine that when the first attention is all you need paper came out, there are a lot of things. And as I explain that, you will see that there are a lot of things it has. And see, frankly, when a paper like this comes through, a breakthrough, there's a lot of experimentation, hack, trying this, trying that. You have a vague idea that this will work, but you don't know what the hyperparameters are. What is the dimensionality you should reduce it to, right? How many layers you will need, like the basic question in neural networks, the perennial question, how many layers, isn't it? So how many layers do you have, and things like that. So a lot of that were experimentally or empirically decided upon to converge onto things that work. And since the original paper, they have changed. So for example, BERT base and BERT large, they use entirely different values. And so the whole thing is fluid. I mean, think of it as simply a hyperparameter of the transformer.
Okay, so does that mean that, for our, understanding, you just take it as square root of 64 there?
Yeah. So you just took a square root of 64.
Okay, so there is no need for us to get into more details as why we got 64 there.
Yeah, see, like I told you, right? It's just a constant. And for understanding, here's a basic tip that I told you guys for understanding anybody's paper or theory. The first thing you do is go erase out all the constants. Then you will be left with the core or the essence of what they have written. And now try to interpret that. So suppose you saw this equation like this. How would you do that? You would say that this, right? It's a v vector. So this is a vector, right? Vi. And so all of those elements are there. This part, what is it? This is a similarity. Then you're doing a softmax of similarity. So what are you doing? You're making it stand out, really stand out, and making it into a 0 to 1 scale. And so what you're doing is you're in some sense taking the weighted amounts of this, different values, right? It almost has a flavor of a weighted average or something like that. So that's what you're doing. Effectively, you're doing some vague way like that, and you're creating your vector. And that is the amazing thing. So that's how it is. Once you get the idea, you get that. So the rest of it is mechanics. If you understand what attention is, now comes the question, how do you do that? And the original paper has some quite a bit of things to it. So a unit. So what you do is, first thing you do is, let me lay it out in the way they laid out. The first thing is you have an embedding. So suppose you have a sentence, the cow jumped over the moon. The beautiful thing is that you have no choice but to give it in parallel. Why? Because what did I do wrong? 5. The cow jumped over the moon. Why did I end up with only 6 words now? Okay, so let's say that this is it.
Oh, the period. The last one is the period, W7.
Period is the W7.
W7.
Upward.
Right, is the separator. All right. So what happens is that because each of these words, each word has a query, it needs to go pay attention to other words, right? So you have no choice but to feed all of these words in parallel to the embedding, but they're independently traversed. But now here's the interesting thing. This embedding is not your word to vec or glove or anything. You say in this neural architecture, let it go and learn what is the best embedding for the words. You feed it lots and lots of words and sentences, and it soon figures out embeddings. And one of the lovely things it does is contextual embedding. It knows how to distinguish between the three meanings of stand, right? It will do it, and it becomes fairly implicit. So this is the word embedding, and then you do a position embedding. So you take the position of the word. And we went into the position embedding quite a bit on the Sunday class. So I don't know if I want to give time to it. I noticed we have spent an hour. But imagine that somehow you need to inject the position information here. The two together, the word embedding and the position, word embedding, position embedding, makes the complete embedding vector for each word, right? Each word embedding vector goes. And then comes the interesting part. The interesting part is it goes through this so-called attention layer or self-attention layer. What it does in simplest form, it multiplies these values. It will take a word. So word embedding, actually, I know that these words I've used W for, which I regret now. I wish I would just use the word. Okay, we will just use that. So what you do is you multiply it with a query matrix Q to this word EI such that it produces the query. So this is just a weight matrix. So think about this. Suppose the dimensionality of this typically is 1024, let's say, right? 1000 dimension, give or take. Now what you want to do is you feed this 1000 dimensional vector, but you want to produce a vector which is only 64 dimension, right? So all the query vectors 64. So what happens? You need a matrix which is 1000 cross 1024 cross 64, isn't it, W? Does that make sense, guys? Right. So you will multiply it with the right matrix of the right shape. And now the whole question is, no, wait a minute. Where did that matrix, what are the values of the matrix? And here the answer in deep learning always is, we don't know, we'll learn it, right? So just create a matrix of the right size, multiply it so that what comes out is some vector which is of the right dimensionality, 64 dimension. Then you train another matrix key such that when it is multiplied to EI, it produces the KI vector. And another, likewise, by now you get the drift matrix such that it produces VI vector, right? And of course, VI, KI, QI all belong to a d-dimensional vector space. Typically, 64 was the original idea initially taken, right? So you end up with these vectors. Are we together? And then what you do is from these, you produce for each of these words, you realize that each word J, you can now produce the attention vector, isn't it, guys? Given the KQV, you can produce out of this, first KQV comes out. KI, QI, VI comes out. Then these things can together produce what? Your attention vectors, right? A1 all the way to A. Suppose there are n words. You will produce all these n vectors. So what happened? 7 words went in and 7 attention vector came out. What do these attention vectors mean? The attention vector for the word cow, right, probably is paying a lot of attention to the word jumped and to the word moon, right? So you will get you have a different attention vector between for each of the words, and the intuition is this. So let's look at the word. Let's say that the cow. Let me write it like in a. Now I'm going to complicate this sentence. The cow ate her treat and crossed the fence and jumped over the moon. Suppose maybe I'll make it even more complicated. I'm just trying to put the sentence on there that Sally gave, right? It jumped over the moon. Then it jumped, maybe then also, then it jumped over the moon. So think about this. All these words are there. The word it is there, right? When you are thinking about the word it, you need to know what is it? Right? What does the word it refer to? And the way we do that is that we make sure that the it attention vector is giving a lot of attention to cow. It's like heavily, most of the weightage is given to the word cow. It is pointing to the cow, that the it refers to the cow. Am I making sense? And of course, every word is paying different levels of attention to it, but I wanted it to stand out because this is crucial. This is ambiguous. Does it refer to the moon? Does it refer to Sally? Which hopefully not. Does it refer to cow? Isn't it? So that is the value of attention. That's why you call it self-attention. The words are paying attention within each other. But at the end of it, what you end up with is everywhere you end up with A1, A2, A7 vectors. And now comes the magical part. So you have one layer of attention. In the first layer, word embeddings went in. And what came out are the attentions, attention vector. Then what you do, because for each word, each token, there is an attention vector, you feed it to another layer of, you do the same game all over again. You make the attention vectors pay attention to, decide how much attention they need to pay to each other, right? So that goes here, that goes, so this goes here, this goes here. And what they found is, for no, I think big reason, but again, one of those things, they just experimented it. They put 6 layers in the original paper, right? And so, but that is not enough. So this entire thing, the word for that is, it's called a head. This is a head in the world of attention. And guys, this, the reason I'm going into this mathematical details is, trust me, this is when people these days go for interview, for some reason, details of this paper tends to come up quite a bit in these, can you explain what this is and so forth. So all of the 6 layers put together is a head. And now here comes the interesting part. You have another number of heads. The total number of heads that are there are 8. I think the original paper used 8 heads. These days they use even more heads. So what it means is that, you know, we had one weight vector, WQ here, but this is associated only with the first head. This will have its entirely different WQ prime associated with the second head, and so on and so forth. Now, why in the world would you complicate your architecture so much? What they found is that it is somewhat like convolutional filters. See, what happens when you use many convolutional filters? Each filter detects optimally something different. One detects, let's say, a vertical edge, another detects a diagonal, and things like that, right? So they all learn to pick up things that the other guy is not picking up. And so the same thinking goes here. The head is somewhat like a convolutional filter, and in a rough analogy. And what you're saying is you need a whole lot of filters so that they all pick up different aspects. So when the words go in, one, maybe if I have to just caricature it a little bit, one is more sensitive to the grammar, one is more sensitive to some other aspect of the sentence, and so on and so forth. So they will pick up on different kinds of signals they'll pick up from the words, and they'll pay different kinds of attention. The words will pay different kinds of attention to each other in the different multi-heads. And at the end of it, all of it put together, and obviously not to forget that there'll be the activation functions and the fully connected layers and so forth. And there will be a joining of these two, and then the residuals, you know, all the things that we have learned in our fundamental deep learning. There is a lot to that. So all of those things are there. Are there residuals there? Yes, they are there. Are there, do we have feed forward layers? Of course we have that. All of that is produced, and the whole thing is called the encoder. And the transformer, the original transformer, is actually fairly complicated. It is made up of 2 things. It produces the encoder. So this is the encoder. basically words go in, right? And I will ignore the position encoding and something. I'll just leave it as that. And with the multi-head and all of that, and layers and layers and layers and fully connected layers, at the end of it, what happens is it will produce the last layer. It will produce its own KQV, right? This is the output of each of the words, KI. You just stop here. Then what they did is they have a decoder, which is very interesting. You take, in the beginning, you have a trigger, which is nothing but a start trigger. You put it through, again, some attention heads, right? So some initial word, you get an encoding of it, right? And what you do then is you put it through a decoder. So this is actually still encoding. Encoding. So decoder actually has encoding built in. These are called masked encoders. And for reasons that I'll make available, explain in a little bit. So what happens is that this is one input, right? So into this attention model, or sort of a self-attention model, the attention, I don't know if you should call it self-attention. I'll just leave it as the word attention. I don't know what the paper calls it, but it's basically the same thing with one interesting caveat. The query from this inside thing, the vector that comes out, you treat it as the query, right? And from the decoder, from the encoder, what you take in is you take in the key and the value, right? So key and value, you think of it as the real summarized thought or encoding of the sentence. Think of it as stored data identified where the coordinates of any value is given by its key, right? You feed the key and the value from the encoder, and you take a query from here, right? By encoding some inputs, a starter input. Let me just call it starter input. Then what will happen is it will produce one word of, let's say, Spanish, the first word of Spanish. Then you do something interesting. In the beginning, you took a dummy token. Now you take this and feed alpha here, right? So alpha and start together will create the query vector. The K and the V's are pretty much frozen. This is your encoded thought vector, is essentially a KVs. Now this query changes, right? You have a different query vector because now it is a composition of alpha and start. It goes into the attention. It will produce another word beta, right? That then next you take that and now you feed alpha and beta into this word to get gamma, right? So your query that here first starts with nothing, right? It's just a token, empty token. Then next time it starts with the first word, the Spanish word that it produced. Next it starts with the alpha beta, right? Next it starts with alpha beta gamma, right? So what happens is as you train this, what happens is suppose you know this, because when you're training, you really know the Spanish that should come out. So suppose the Spanish was alpha, beta, gamma, delta, epsilon. What are you doing? When you want to train it on alpha, you're masking this all. Masked is everything. Alpha, beta, gamma, delta. They're all masked. In this case, masked is, while training it, you're masking only beta, gamma, delta, epsilon. And then here you're marking. So in other words, whatever word there is, you're masking all things to the right of it. And you're only looking to the left of it, isn't it? So suppose you want to, you're at gamma and you're looking to produce delta. So obviously your delta and epsilon at that moment are masked. And you're saying that I'm feeding alpha, beta, gamma to produce the query vector, and that's what it is. So it is called, that's why it's called the masked encoder, right? Mask or mask attention. People often, I'll have to look at the exact word, use mask attention. And then you feed it in and you go away. And so when you look at this architecture, the first thing that occurs to you is, my goodness, isn't it? There's a lot happening in this particular paper and this particular, and it must have arisen from a lot of experimentation, and trying things out and doing it. And obviously this had a profound impact on natural language processing. It is commonly believed that it was a watershed moment. After that, NLP, the effectiveness of MLP went up significantly in many, many areas. And the whole way we write codes changed. We use transformers now. So I talked about, for example, I taught you glove and this and that, but now I'm saying, hey, you just learn the encoding as part of the transformer training itself. And the most remarkable training is all of these W vectors even within a head, there are 6 layers of W query vectors. Then there are 6 matrices of key vectors, then 6 matrices of value vectors. And that is just within one head. And if you have 8 heads, now you go multiplied by 8, right? So you realize that there are 48 query weight matrices and another 48 this key and for value. And so by the time you're looking at it, 150, just 150 matrices are there to learn. And each matrix is approximately 1000 by 64. So you realize that it's a pretty huge model. Lot of training to be done in this model. And that happens. When you train the transformer, it's not easy. You need to feed in a lot of data, and then it sort of gets trained. It's very hard to train it from scratch if you don't have sufficiently many data. So what we do typically is we start with a model of a finite size. You take a pre-trained model. That model is the transfer learning concept. And really, that is the way to go. You take a model, you chop off the last layer. And when you do this thing, by the way, you can now use it for all sorts of purposes. So you can then, for your problem, just apply, first apply directly to your problem by applying a classifier or whatever it is, the last layer to it at the head, or maybe fine tune it, relax a few layers, let it get trained, or maybe relax it and get it trained, but start not with a blank slate, but start with a pre-trained model and let it just fine tune its weights when you train it on the data that you actually have. Right? These transformers are trained typically on massive machines using vast amounts of web data. Right? So usually you don't want to train a transformer from scratch unless you truly have a huge amount of data. What you want to do is you want to take the transformer and do the last mile training for your particular domain. And it works very well. So guys, this is the concept of attention and transformer. I know that I took you through a long theoretical journey today, and you might wonder that what was the whole point of it. It is the thing, guys, is practically in NLP, it is the big gorilla at this particular moment, and there are lots and lots of variations and implementations of the transformer. I thought it was worth it for us to understand all of these words. These words get thrown around quite a bit: attention, self-attention, transformer, etc., etc. So that is that. We are coming upon a break. We are more than 1.5 hours through. Let's take a 20 minutes break. But before I do that, any questions, guys? Did you understand, by the way? For many of you, it was a repetition. I hope it wasn't a useless repetition.
See, if I have one question on understanding the purpose of the multiple heads. So there were 6 layers.
Making one.
Yeah, in one head, and there were 8 heads, right? Now, could you give us the intuition in terms of when the training process happens?
See what
Why
happens.
would each, I'll put the question out completely there. See, when the training happens, why would each of the heads learn something different? Where is that difference being built?
Yes, it's a very good question. See, what happens is it goes back to our convolutionals. Like, oh, but you didn't take the CNN. You didn't take part. Did you take part 1? You took part 1, right, Premji?
Yeah, I was there. Yeah.
You were there through the whole of part 1. Okay. So remember, we talked about the convolutional filters, right? So what happened? In the world of image processing, people used to hand build filters. It is a good idea to look for vertical edges. It's a good idea to look for horizontal, or look for this or look for that. There's basic primitives in the first layer when you encounter an image and you go over the image with that filter, you scan it. It's like a stencil, cut out. I'm looking for this shape. Is it there? Right. And the field was that when deep learning came up, it basically said, you know what, let us just use this thing, neural network, let it learn the filter weights. So the question naturally arose, well, if I have three filters, won't all the three filters shown the same image, won't they learn the same thing? But that is where the gradient descent and the loss function magic comes in. See, what happens is when you back propagate, if two filters learn exactly the same thing, there is redundancy, right? So let us say that they have learned something and the loss has come down a certain level. But the moment one filter, even with a small fluctuation, learns something different, its values change, what will happen then? Quickly, it will move in a direction in which it's picking up something new, and then the overall loss is coming down, the training loss is coming down, and it will drift, and soon the two will become almost as, they'll become as different as possible. They will pick up different things from the system, from the image, literally different things, because it's almost as though they're talking. I am taking care of this, you don't take care of this. Right? You take care of something else. But it has to do with the magic of, very straightforward magic of gradient descent and loss. See, the moment you keep pushing down the loss, right, at the end of the day, these filters, in some sense, they have to become orthogonal to each other. Otherwise, if there's redundancy, there is not enough learning. But there is, the mechanism to learning is there, it's just being wasted. So soon the training will force them to diverge. In fact, they never converge. I just took the example, what if they started aligned? That was only theoretically. In reality, these filters will start with random values. And gradually, as they take shape, their weights move, they will all end up with orthogonal things. They'll pick up literally different kinds of signals. So that's what happens with convolutions. And the idea is that each of these heads is like a convolutional filter. And these multi-heads, see, these multi-heads are acting in parallel, right? Each of the heads has its own, the same words are going through it. But as the training happens, the loss minimization process and all of this gradient will force these heads to learn literally different things so that they don't repeat what the other guy has done, because then you don't minimize, you're wasting resources, right? So they learn different things. And so also within a head, the information flows sequentially. Attention of one layer goes into the, gets into its next breakdown into KQV and so on and so forth. It keeps propagating forward. But the point is multi-head. These heads are completely independent of each other. They're like the filters. They all are doing their learning independently. But because of the magic of this optimization process, the random weights will flow in opposite directions. They will sort of make sure that they learn different things.
Okay.
And that is it. See, ultimately, this is the magic. It is all calculus. That's all, calculus, linear algebra, matrices, and so forth. But this whole thing works. Right?
Okay. I think I might come back to this question again later. I'm taking it for granted right now, and then let's move on, right?
Yeah, it takes you, see, when you think about why or how these things work, it does take a lot of thinking just to figure out why in the world did it work, right?
And can that not be practically checked also by having, let's say, less number of heads and then increasing the number of heads and saying that the loss?
I'm sorry, please say that again.
No, what Premjit is asking, can that not be practically checked also, that you have very less number of heads and that loss may be more, and as you increase the number of heads, you will lose?
Oh, absolutely, Sanjay, absolutely. So see, somebody must have had a eureka moment. Let's add one more head and gotten even more accuracy or even better performance, right? So you can imagine that these things are team effort. So people must have been trying different things and the whole thing is experimentally. I mean, there's a lot of experimentation before you come up with an architecture like that. What you don't see in papers are all the ways that didn't work, right? Or the halfway steps that you have to talk to people to figure out to get the history of it. But any good paper is a result of months, sometimes years of effort, and
So,
often it's a large team effort.
so as if in the practical context, when let's say in your company, when you're using one of these transformers, would you ever tweak any of the number of heads or so on, or you take that and then just work a few things on the last layer alone?
No, no, no. What happens is, see, imagine that the weights are trained.
Hmm.
Your problem still deals with words. The language is still English. So a lot of the learning that the transformer has done is still applicable. So if you just try to retrain the whole network transformer, but you start with a pre-trained transformer, what will happen is those weights will just jiggle a little bit and adapt to your problem. But what you're not doing is, learning all the weights from random values. They're already near perfect for most problems.
Yeah. So let me rephrase the question as if like, so we had eight heads, six attention layers, right? Now, when you say you will retrain something, what would that be? Would you drop a head or would you drop?
No, 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 no. You don't do that. What you do is you take the transformer. First of all, you don't you freeze the transformer. But at the end of the transformer, you'll put your normal classifier, right?
Okay, okay.
Right. So that classifier needs to be trained. So you'll screw in a classifier at the end of the transformer, and you say, okay, this is my model. But then that classifier needs to be trained. You'll train it, see how the performance is.
Okay.
Suppose you say that maybe there is scope for improvement. If you have enough data, then you say, okay, let me unfreeze the transformer.
Okay.
And epochs and see does the fine-tuning get incremental very much at this moment. While we have a certain amount of theory, in practice there's a lot of experimenting with things, seeing that they work, and then once they work, now sitting back and saying, why did this work? Post hoc reasoning in this field.
Okay. Thank you.
You're welcome. All right, guys, if there are no thoughts, it is 8:40, 8:40, 50. We should take, by the way, those of you who have been through, I mean, you guys have all been through the earlier transformer talk. I deliberately talked about it differently. Was it useful, or you felt that it was quite repetitive? How do you guys feel about it?
Yes, Asif, it's useful. Very
This is
useful.
useful. Yeah.
Okay, good. So, so this is it. Actually, it's one of the things. It takes time. Like, what is attention? Right? Our papers are written very condensed, and a lot of people have explained, but I sometimes feel that some explanations are very, very good, but some explanations just repeat the words from the paper. And it is worth asking, what is this KQV and things like that. So, all right, guys, it is 8:50. Let us regroup. I'll stop the recording. We will come back. And then we will take a practical example of a transformer. Maybe I'll talk about BERT. Make sense?
Okay. What time
Is
are we
20
going?
minutes enough? So that is a question actually. Is 20 minutes enough, or should we make it 30 minutes? Should we come back at 9:20 so we can all have dinner?
9:20.
9:20 is okay.
Okay, let's make it 9:20. We'll have half an hour.
Okay. All right.
All right.
Asif, this is Balaji. Asif, I had a quick question. Is it okay?
Yes, please go ahead.
So, Asif, initially I saw you say that the words like are in English and they need word to vec kind of a thing to get encoded into some a meaningful digits, like meaningful information. But
Right.
here we are not doing that. Instead, the whole flow is going to get trained and it's going to create its own vector. That part I didn't
See,
clearly understand.
think about it this way. You have a neural architecture to train the word embeddings, right? Remember the word to.
Yes.
So what here we do is that we don't train the word embedding using skipgram. Instead, what we do is that neural architecture, you just put it in the front of the first step in the transformer, and you put all the
Uh-huh.
word to it, right? And
Mhm.
you let it flow to its eventual task. And whatever embedding, it is again the same embedding. It will pick up whatever 512 dimensional embedding, right?
Uh-huh.
Like what to make or something like that. It will do the same thing, but you train that embedding right there in the
Mhm.
transformer itself, custom train it. You don't take a pre-trained, more general purpose embedding. That's all.
Oh, I see. Because I was thinking without the words having any meaningful transformation to
Mm.
start with, how will the attention be of, I know, so it's like almost there's a big training phase through
Yes,
which all these things are learned. Oh,
yes, yes. Huge, huge
that's
phase.
it's difficult to wrap the, I
Yeah.
mean, hopefully there are some examples to which I might be able to understand.
Isn't it remarkable that this transformer, there is so much going into it, so much training. And when we do this particular one, I'm talking about BERT, which is by
Uh-huh.
far the most popular, you will realize
I see.
how enormous these models are. We'll do
Wow.
in a little. These are just more. It is not something that you and I can train. That's the bad news. It is only from scratch. We can't. It is only something that can be done on gorilla machines or clusters by people
Okay.
with deep pockets and lot of time on their hands. People who can throw pretty much all of Wikipedia and all of every written word of the English language into the or any language into the mix, right? And
I
then
see.
get trained.
And so, anything other than the translation that I know all these architectures are explained using translation as an example
We'll do more
application.
examples today, no? Like in the second half, we will do quite a few examples.
Sure,
Yes.
not just translation, but something other than translation also.
Yeah, yeah, yeah. In fact, I won't talk about translation. I'll talk about something else. Question
I know
answer.
it's easy for us to understand with translation, but I'm trying to see like would there be any other application? But yeah, I
Yes,
will
yes.
wait for it.
Okay. Classifier, they can be used as classifier. They can be used to extract keywords. They can be used for sentiment analysis. They can be used for, like we use it for literally text summarization. You have a long,
Okay.
you summarize it. The uses of transformer are huge. See, when you introduce the subject of transformer, taking the encoder decoder sort of makes it easy to understand what is going on. But once you have understood, then the field is vast.
I see. And when you say that you can plug out the last layer and retrain, would it really matter if the transformer is trained for translation and then you take it and then you slice out the last layer to retrain it for a different purpose? Is
Yeah,
that
you can do that. What you do is you download these pre-trained models, and then you train it one. You have multiple copies of it. You train one for translation, the last mile journey, another for classification, another for
ah,
summarization. So you screw in different heads to them,
got
yeah,
it?
the last pieces to them, and use it differently.
So the 90% of the architecture remains the same, which is understanding the language, and then the last 10 is the usability of that architecture.
Yeah,
Something. Okay.
it's
Okay.
just
I
last.
see. Thanks.
Nice. Very good.
Asif, this is a good question and answer between you and Balaji. I think I just came back after a bit of gap. So I think I got some portion about like there was last portion what we were explaining the faces, etc. I got lost. You asked the question, but I thought it's too late to ask that question.
What was the faces question?
Yeah, so you started drawing like 7 words going parallel into the box. At that point, I lost. Like
The idea is that, see, there's a whole sequence of 7 words, right?
Yeah.
They all go in, and each of these words are now paying attention to each other, different amounts of attention to each other.
Correct.
That's it. Right. And that attention, like for example, when we come to the sentence, the cow jumped over the fence, then it.
Yeah,
What
so,
does
so,
it refer to?
yeah, so cow and it has more proximity.
Exactly, more
Yeah.
similarity. And attention in very simple terms, right, is similarity weighted values. It's just weighted average in many ways. One rough, easy way to think of it is in some ways, it's just weighted average.
Okay. But then you had 2 boxes, right? Like I was just watching a little bit on and off. So there are 2 boxes. And then you said you had encoders, and you had other box encode alpha feeding into the main box. I just couldn't.
Oh, the whole architecture of
Yeah.
the transformer. Actually, yes. I will let me explain that. I'll share my screen.
Yeah.
Actually, can you give me just 5 minutes? I need to rest.
Sure. Okay.
But I'll go back and re-explain when I start explaining
That'll
again.
be great. Thank you.
Right. All right, folks, we are back. Are we all back? I hope so. I'm resuming the recording. Huh? So first, we'll take up the question that you asked. Shini, go ahead.
Yep.
So which part are you referring to?
So if you come down,
1 second.
I think I understand this soft max a little bit now.
Yeah.
But then what I was lost on this, this diagram, encoder, and then these two boxes.
Yeah. So let me explain that. So words go in here. In let's say one way to think of it is, let's say that English sentence goes in here, right? What will happen is that whole sentence will produce its k vector, v vector, and the q, right, at the end of it. So now we have to translate that one sentence. What happens is, this is the encoder part, this is the decoder part, right? The right hand side. So the decoder works in an interesting way. You only take the key and value, not the query, not the probes. You take the key and value and you feed it into one attention layer. But then the question is, if we are going to do that here, we need the Q also, right, to create the attention, because attention needs K, Q, V, right, softmax. So where is the Q? And that answer to that Q is, what you do is you create an encoding layer here, a few attention layers. These are called masked attention layers for a reason. What you do is, in the beginning, you just give it a dummy token. So it will take a dummy token as a word, a single word, and it will create its own KQV. Throw away the K and Q. Just take the Q, KV, take the Q, and you take the K and V coming from the encoder.
Okay.
And now you have a Q. So you can go ahead and produce some word, right? You can go ahead and encode and ultimately apply some classifier, fully connected layers, and the usual thing. So you come to the conclusion that alpha is the best Spanish word to produce. You go ahead and produce it based on the attention, right? Then once you have produced alpha, now what you do is you take alpha, and the next time around, it becomes, this is the recurrent part. You put it again, and now you feed alpha into this lower box, this masked attention. You feed alpha into it. So alpha will go in, again, it will go and meet the K and V, which is coming from the encoders, which are pretty much at this moment constant. And then this attention layers will do its attention business, and it will ultimately point to a new Spanish word, beta, right? So beta gets produced. Now you take both alpha and beta and put it here, feed it back into the system, and you go through the same thing. See, what you do is, as the Spanish words are being emitted, that partial sentence becomes the input here at this level, at the bottom, to the decoder. So the decoder input starts with the partial translated word as well as the encoded sentence coming from the encoder of the original language. The KV comes from there and the Q comes from here.
But the KV is going to be constant, right? When you loop.
Going to be constant. Yes,
okay.
That's it.
But you'll be looking through alpha, beta, gamma. Where do we stop?
What's that?
So your K and V are constant to the decoder box, right?
Right.
And your decoder box is looping around.
Yes.
First it produces alpha.
Yes.
You feed the alpha into this again to produce Q. Let's say Q prime.
Yeah.
And then that works with KV.
That's right.
This is beta. And then now you got alpha and beta.
Yeah.
So when do you stop it? Like this is.
It will ultimately emit the stop token.
Okay.
When the stop token is emitted, you stop. The sentence is done.
But how will it produce the stop token? Because you only pass K and V, right? So
here's the thing. A KV are coming from here, right?
Yeah.
That is okay. They remain constant. As you keep feeding alpha, beta at the bottom, what are they doing? They're generating the probe or the query, right? Or query vector. Each probe or query vector will go and match this value vectors based on the key dot product. It will be similar to some key. different query vectors will be similar to different keys, because if in the beginning the query vector was nothing, it's just one start token. Then it is start and alpha. Then it is start alpha beta. Then it is start alpha beta gamma. You see that, right? So what happens is that as you keep feeding all of that in through this layer, you keep producing the query, different query vectors. Eventually, this query vector at some point will produce, let's say that there is a epsilon is the last word. Once you feed this entire sequence, this decoder, it will start pointing to the end of sentence. The next word that it will produce is end of sentence. Right? And the moment it produces end of sentence, you say, okay, fine, you're done.
Okay.
So Asif, I think intuitively something is missing, right, in that interpretation.
Because it's the same, right? Because I saw K and V, Asif. It's for, let's say, for first two, the cow, and then the K and V are for those two words. And how can I get to the end of sentence from those two?
See, all the KVs are there. K1 to K7 are here. V1 to V7 are here.
Okay.
All of them are being passed. Remember, K, when I wrote K, I wrote it more as a matrix. All the Ks and all the Vs are being passed.
Oh, okay. So you're passing the complete matrix of K and V. Okay,
exactly.
That's why I was asking the question, right? Are we passing the whole matrix or just passing K and V?
What happens is that K1, K2, these are vectors. And then, of course, the K itself, in the literature, right, they often use capital letters for matrices. Okay. So I pointed out that there's capital. Remember that I use little k for vector Ki. But then capital K when you use, or V when you use like this with caps, it's just an implicit convention that you treat it as a matrix. It means that it is all of those vectors put together. Right?
Because of this vector, it will get to the end of statement. Okay.
All right, guys. So now what I will talk about is one particular, a very popular implementation, two actually. So what happens is, you notice that this is a pretty complicated transformer architecture. So two interesting things came out. One is GPT, and it's very GPT, GPT-2. Now, of course, the whole world is completely excited and frightened by GPT-3. What the GPTs use is, they only use the decoder part of the architecture. And what they do is they don't have one decoder, they go on stacking decoders. So I won't go more into the GPT because I had to pick one and go deeper into it. So we picked BERT because BERT is something you'll use quite a lot. Right? So this. On the other hand, if you just don't throw away all the decoders and you stick to only the encoder part of the transformer and you just go on stacking a lot of the encoder, that's it. You get something called the BERT. Bidirectional, etc., etc. But I won't go into the full name. I have to myself keep reminding myself what is the full name, and the full name is, hang on, I will remember. I have to look it up myself.
Bidirectional encoder representation from transformer.
Yeah, this is it. A BERT, pre-training of deep bidirectional transformers for language model. Okay, this is it. BERT, bidirectional transformers. So we will do BERT. So what does BERT do? BERT is an interesting thing, actually. When it was created, it came from the Google AI language lab. When it was created, it became quite another sort of a success moment for the transformer story, big success moment, because what they showed is if you use BERT as a transformer, a lot of the common things that you could do. So let's think about the common things you can do. Take off a pair of sequences, sequence alpha, sequence beta, right? You train it using this sequence, and then you can have some output. So let's think what are the common things you can do. First of all, if you just don't, sequence beta. So suppose sequence beta is not there. You have just sequence alpha and a null. You could do, for example, sentence, like a sentiment analysis. You could just How? By attaching a classifier at the end of it, at the end of the transformer, right? You could do, for example, sentence completion. So for example, you can ask, if this sentence alpha is there, what is the best beta that completes it? Right? What is the best sentence that follows it? So what does that do? That gives you generation, right? Next sentence, next sentence, the next sentence generation or completion or something like that, right? Next sentence completion, it gives you. Or you could ask this question, suppose I have S alpha and I give you a choice, A, a P, Q, R, S, many sentences, but only one of them follows from this. It's an entailment question, it's called. That so I went to the coffee shop, and the sentence would be and bought myself a cup of coffee. That would probably be a good following sentence, as opposed to and the cow jumped over the moon, right? Or and the something else, some arbitrary sentences. So you can train the transformer to pick this because it is just a thing of all of these. You train it with, you say this is a positive case and the ones that are wrong are the negative cases. So now you can train it just the way you train classifiers or things like that, and you can make the transformers do all sorts of things, right? Things like that. So the transformers, when you went to the transformer website, the Hugging Faces, we did the lab, if you remember, and there were many applications. We used it not just for language translation, but we used it for many, many purposes. So these transformers can be used for many purposes, in particular BERT. So when you train BERT, the two things you do, you only take the encoder layers, lots of encoder attention layers. And how many attention layers? Now, one of you asked this question, why 8 heads and why 6 layers? And the thing that I wanted to mention is, there's nothing magical about it. So let me show you what it becomes. I will, hang on. Let me do this. Somewhere in here in the paper is a discussion of how many it is. Yes. So what they did is, there are two models of BERT or transformer they trained. One is the base model, one is the large model. So here, if you look at it, the number of layers, see, remember we said that there are 6 layers in the original transformer model. Do you guys remember? We're talking about it. In any head, there were 6 layers, 6 attention layers. So here in the BERT base, they started with 12 layers. Then in the original one, the hidden representation was 64 dimensions. Here it is a huge 768 dimensional representation. Do you see that? The hidden, right? The hidden size is 768. Huge. And how many? So when we talked about multi-heads, how many heads are there? 12 heads. And so this entire model with their many layers has 110 million parameters. So guys, just think for a moment what that means. If you remember, you all started your workshops with me. We started our journey with linear regression, and there used to be what, 1, 2, 3, or maybe up to 10 parameters, 10 dimensional or 20 parameters. Do you remember Boston? The Boston crime data and so on and so forth, and all of those data sets, California housing data. There were like 10, 20 dimensional things. If you made linear models, they would have 10, 20 parameters. Guys, do you remember those days?
Yes, sir.
Yes, yes.
Yes.
So see where we are now. The state of the art these days is the smallest BERT model has 110 million parameters. A more useful, larger version of BERT, it has 24 layers per head. And the internal representation is 1024, like basically 1,000 dimensional representation. And there are 16 attention heads. The end result is the total parameters that you get is 340 million, right? And now we are talking about models like GPT-3, which are apparently so big you can't even have it on your machine, right? So these models have become ginormous. Somebody, I don't know how valid it is, but somewhere I read, and I hope I'm not misquoting it, that the amount of energy needed to train one of these giant transformer models is about the same as the energy that is used to build about 100 cars and let those cars live out their entire lifetime of gasoline consumption. Think about it. How much energy goes into manufacturing a car, and then in its lifetime of 20 years that it runs, how much gasoline it consumes. And now take 100 of those. That much energy, electricity ultimately goes in training these transformer models. So this is where AI is currently.
As if GPT-3 is 175 billion parameters.
Yes, 175 billion. It just adds more, goes on adding 2, 3 orders of magnitude to it. Shocking, right? Just think about it. It's so big you can't even download it. So anyway, what is BERT architecture? What I will explain to you is the BERT architecture was trained in a very interesting way. It used unsupervised learning. It didn't use labeled data and train it. It actually did something quite remarkable. And it used two things: next sentence prediction and masked language model. These two tasks it used to train a BERT, which is only made up of encoders, no decoders, layers of encoder. So how did they do it? Right? What you do, and I'll just explain it on a piece of paper because then it is much easier. So you take this sentence: the happy cow jumped over the moon. The masked language model, right? I think there's a word close or something like that is an old literary word. This paper mentions it. I keep forgetting. But masked language model, what it basically says is that in the first bit, you take a sentence, and maybe you can take, because we take pairs of sentence if you want, alpha, beta, you can take pairs, 2 sentences with a separator. And what you do in a BERT is you always start it with not only a ending of a sentence, but the entire sequence you start with a special token that is called CLS. Now, why the word CLS? Because quite often this token, the final representation of this token as it goes through the encoder, you feed into a classifier for some of the tasks and so forth. So that's why the word has stuck to it, the CLS. So now you have this token, all of these tokens. What you do is you randomly go and you mask some word, you hide it. So let's say that you go and hide it. Are we together? Right? You hide this. Maybe this sentence is too small to hide more than one. So let me take this example. You hide one word. Then what happens is you pass it through the transformer layer, right? A transformer encoder layer. And what will happen? Each word will have its final output. Encoding will produce a final output for each of these words. So let's say that it will be A1, A0 for CLS, A1, A2, all the way to A7, right? It will produce. So then what happens is you ask this word 1, 2, 3, 4. So A4. You feed it. Now you can do your normal thing. You can feed it into a softmax, right? Classifier, and see which word in the vocabulary, the target variable are all the words in the vocabulary, which of the words it is pointing to, right? So for example, is it pointing to the word truck? Is it pointing to the word house? Or is it pointing to the word jumped? Right? And the idea is if you train it like this, you want to make sure that it points to this word. You train it in such a way by masking some words and making it guess it. the more it guesses the correct word, the more it gets trained. All those parameters get trained. So that is one task. Now you notice something very interesting about this task, that there is no label data you're waiting for. You're literally creating your own label data. You just take vast amounts of text. Just go take Wikipedia text, right? And what you do is it is filled with sentence. I think it is like 150,000 million words or something like that, ginormous number of words, and lots of sentences. And you play this game of masking some words and making the transformer learn it. And then gradually those parameters will start learning. And so what happens is when you take a really long sequences, you imagine long say, you go and mask 15% of the words, right? And you don't just mask it. Sometimes what you do is you play games. Instead of masking it, sometimes you go and replace it with a random word, right? And yet you expect that for that random word, the output will point to the correct word, right? So you either mask it, you altogether mask it, or you put a random word and things like that. You play these games, but at the end of it, what happens is that so 15% word masking is what the original paper did, Bird paper did, and they got very good results. Then the second thing they did is the pairing problem, right? Next sentence prediction. So this is again very easy. You can do, and so you don't need vast amounts of label data. You go to Wikipedia, you find a sentence: the cow jumped over the moon. Somebody remind me, what's the next sentence, Kate? Kate, what's the next sentence? Or anybody remembers? And there is something ran away with the I don't know what. So anyway, so suppose there is another sentence.
The dish ran away with the spoon.
Yeah, the dish ran away with the spoon. Dish ran away with the spoon. So what you do is you first, this data, this is S1, S2. What's the next sentence? Sorry.
Oh, the next sentence you have there is the dish ran away with the spoon.
Okay.
Dish ran away with the spoon.
So suppose there is another. Yeah. So this is the correct. So what you would do is you would take a valid two sentences that follow each other, treat it as a positive result. Output is positive, and then you would take S1 and just put some garbage like random sentences taken from the corpus. S random. And then you would just create a lot of random. Typically, I think for every correct sentence they throw in 5 random sentences. You mark them as negative, right? So now what do you have? You have essentially created label data of your own, isn't it? This is the input, this is the output or the target, and then you start predicting that. So what happens is by the time this model gets trained, you can tell whether sentence, given a pair of sentences, it can tell whether S2 follows S1 or not, right? So this is the second thing that you use for this purpose. You keep predicting that. So these are just means to train the bird. I won't go more into that. At the end of the day, what happens is the bird got trained, and there is a benchmark called Blue. And there are quite a few tasks. Basically, the rest is history. It turns out that it went and wiped the slate clean. It won it won almost all the benchmarks suddenly in one shot. And so BERT has become obviously a runaway success. A lot of people are using it in a lot of different contexts. In my team, we use BERT quite a lot, variants of BERTs quite a lot, and for all sorts of purposes. And the good news, guys, is this was the theory. This is theory worth learning once in your lifetime. And I really feel that you should learn it because for multiple reasons, you should know what it is that we are doing. And secondly, for those of you who will be job hunting, these are some rather common questions that keep coming up in interviews, right? somehow transformers and attentions for, I suppose, valid reasons. They are a staple diet of interviews to explain how they work and so on and so forth. So it is worth knowing that, and now you guys know that. Now in the lab part, if you remember when we did the lab with transformers, it was perhaps one of the easiest labs because there were already pre-trained models. We just used it and got away with so much functionality, just freebies. That's the power of transformers. But there is a other side to it also, which is that we can use it to do more complicated things in which we actually train the transformer. So in the coming weeks, we will deal with a little bit harder problems where we take the transformer and we don't just use it out of the box as a pre-trained model, but we do fine tuning of the transformer for our specific purposes. And we'll take a variety of NLP tasks and we'll apply it to that. Does it make sense, guys? So this is all that there is to this transform. I mean, there are a little bit of details you can hop across and so on and so forth. So, for example, when you do sentiment analysis, so you have this sentence, right? The cow jumped over the moon. Cow jumped over the moon. And what happens is you put a CLS token, and the second sentence will be just null, empty sentence. You feed this as input to your bird, and then you're doing a sentiment analysis. What will you do? You need to feed one vector as input. Remember, a classifier takes X vector as input, and it produces a Y hat, which will be positive or negative, let's say for sentiment. I'm just taking an example, simple example. But then each of these tokens are producing their own vector. So which vector we will take? So this is the convention. This is why we put this extra block in the beginning. We ignore the output of all the actual words, and we instead take the output of this CLS token as the input to our classifier, and always work with that. Right.
So what is CLS token? Like,
it is just a token we insert in the beginning of a sentence while we feed it into the transformer. And when it comes out already transformed and all sorts of attention and everything, fully through all of those layers, we use that thing. Now, another thing is, why would you use that? The thing is that the reason you place that block is, it is sort of paying attention to the whole sentence, right? And in some sense, it contains the essence of the sentence. Right. And so that becomes our input vector, goes into the classifier, and then you can use it for, let's say, sentiment analysis or all sorts of things, right? For example, at this moment, I'm trying to train, we are actually, I shouldn't use the word, my team is trying to train, see if we can take texts which are very opinion heavy and texts which are very knowledge heavy and try to differentiate between the two. Right. So we have some early success. Let's see how it all works out. So we do all sorts of things. People use it everywhere. And in the next 2 weeks, I'll give you guys a flavor of the kind of things you can do with transformers.
So, Asif, can you take a moment to explain, like you said at your company, you're using GPT, right? But
GPT-2. We are
GPT-2. Okay. So the part that I was getting to is, we know GPT-3 definitely cannot be downloaded. It's like 1 billion records in terms of the billion weights in
125 billion weights.
So when you're working with it in your company, what would be let's say the computational complexity of doing any change with it in terms of time or computational resources needed? What's the magnitude you're describing there?
We do stick in the transformers and we do train them or fine tune them for our tasks and for many tasks, especially for classifications, for our specific classifications. We do the tuning and the stuff. Generally, it can take anywhere between, some of them train pretty fast. The data is very clean, signal is very obvious. In half an hour, they'll get trained. Sometimes it runs for the better part of 2-3 days on powerful hardware.
So the back propagation, does it go through all these weights?
Everything. Back propagation is the one trick in the game.
Okay.
It's all. See, in this deep learning, right, pretty much the back propagation is the king of the optimization process of this optimizers. There are certain methods that have recently been proposed, predictive coding and things like that, which researchers are showing are equivalent to backprop and are closer to neurobiology. So one of the problems with backprop is the see it's backward and forward, right? In our neurons, signals can go backward and forward. Forward is the prediction path or the inference part. Backward is the learning part. Updating of the weights. But in biological systems, signal goes only one way through a nerve. It doesn't go bidirectionally. Right? So one of the things that people have wondered is that while it works very well, backprop mathematically, how do we build something equivalent that is biologically plausible? Right? And so there are some alternatives people have come up with, and they have shown that it works. But leaving that entire area of research aside, pretty much you have to make sure that throughout your end-to-end system, back propagations the gradients can propagate all the way back. If they get bottlenecked, then you have a problem.
And the computational resource that you allocate for these kind of problems, how would you describe those computational resources?
See, in my team, right, they're very GCP heavy. So they will all go and pick up these GCP instances where you can configure your GPUs or TPUs. And the way we do that is we expand the hardware based on need. If we notice a computation is taking too much, then we add more GPUs, more GPUs, more GPUs. And they get very expensive. Ultimately, you end up paying $10, $15 an hour. And imagine a computation that runs for
3 days.
Yeah, you already run a few $100s through that. And now you imagine a team of about 20, guys, each of them fiddling around with something and running their model. You realize that suddenly the costs are very high. So when you do that, my experience has been that it's cheaper to buy hardware for development, take it to production for inference in GCP. But if you can afford to put hardware under people's desk or something, or in your premise, it is far cheaper. The per hour cost amortized over the cost of the hardware comes out much cheaper. You pay a capital expense, but it is much cheaper. Which is one reason these guys who make this Lambda Labs, etc., they are selling their machines like hotcake. A lot of people are selling a lot of hardware. NVIDIA charges for one of its hardware, some ridiculously high price, $150,000, $200,000 for one machine. And they get away with it because even at that price, when you amortize it over the lifetime of the machine, it turns out cheaper than the cloud. So that's how it is. At this moment, the cloud is expensive. You don't feel it. It's a nickel and diming business. When you're doing little things and learning, it feels cheap. The moment you make heavy use of the cloud, that's when the cost comes. So inference, you want to go to production with your application in the cloud. It's a given these days. Otherwise, people don't take you seriously as a company. Right? Quite often, I don't know why, it's become like that. It's sort of a indoctrination that you must be in the cloud. So you go to production in the cloud. Yes, you do get a lot of facilities, a lot. You basically save on IT resource, IT staff. You don't need your own IT staff, big IT staff. You can have a much smaller IT staff. And you're basically buying IT services from Google or Google and Amazon and so forth. But it's expensive. Right? So go to production in the cloud, my advice. Do your development on something that you can actually see and touch. It will also be less headache. See, when you have a machine that's totally in your control, right, and other users are not logging in, not so weird things are happening. See, this was the industry worked with one engineer, one workstation. So my argument is that should continue in the deep learning world too. At the end of the day, Like, for example, you notice that the code tends to run on my machine, but we have this problem when I give the same code to you guys. Different people have different issues. Right? So at the end of the day, like in my case, I don't get much time. I have a full day job, so then I like to teach in the evening, but I have only limited time to give to it. So when I sit down to write code, I need to make sure that the first time itself I'll get it right. I won't be fighting the environment itself. And it helps to have a very powerful machine. Some of you who work at support vectors know my white elephant and black elephant. Patrick, you know it very well.
Yes, Asif.
All
Oh,
right.
Asif. Hello, Asif.
Yes.
So regarding explainability, Asif, is there any way we could still salvage some form of explainability by building something in the last few layers?
Yeah, it is an area of active investigation. See, some people, even people often used to say, throw in the towel. You can't explain what a deep learning model is doing. It's too black boxy, right? In fact, some people even used to postulate. In physics, there is something called the Heisenberg uncertainty principle, which says that for elementary particle, if you know its position reasonably well, you won't know its momentum, its speed, right? If you know the momentum, how fast it's going, you won't be able to tell where it is with accuracy. So so people often used to pose that maybe we have our own uncertainty principle here in deep learning, in machine learning world. Either the model, if you can explain the model reasonably, what the model is doing, it probably doesn't have that much accuracy or performance. But if the model is high performance, then probably you have lost interpretability. So a lot of people talk like that. I don't know if I completely agree. I personally don't agree, actually. I believe that everything is a work in progress. We need to build tools to explain it. There is a lot of research going into interpretable AI. If you remember, I said I started this workshop by saying I'll put a lot of emphasis on interpretable AI, right? And automated machine learning. Both of these things at this moment seems a little bit distant because we have a lot of material to cover and we don't seem to be reaching to those points. So it becomes a choice. Do I do interpretable AI and automated machine learning, or do we do time series, for example? So we have to make certain sacrifices because we have only 5 more weeks left. But maybe I'll make it some extra sessions after that. But interpretability is big, otherwise society is doomed. We don't know what these black boxes are doing. They're destroying. I mean, so anyway, let me just stop the recording before we talk more. 1 second. So as you guys know, I don't know, some of you, have you seen the movie The Social Dilemma?
Yes, Asif, in Netflix.
Yeah, that's right. I would highly recommend that you guys see it. What is happening is that these giant inference engines are deployed. They are making recommendations. They're doing that. And what these things are doing, nobody really fully understands. So what happens is that when you scale it out at that level, at the scale of global humanity, they are beginning to control people's lives. One typical example is in California. If you say global warming is in Google search bar, it will autocomplete will suggest articles that say global warming is a serious problem. Now you go to Midwest, right? And maybe Missouri or somewhere. There you go and type the same sentence, and it will say global warming is, and it will autocomplete it with the word hoax. And it will show all sorts of articles that will justify and prove and produce evidence saying this entire thing is a conspiracy and a hoax. Right? So what is happening is that, are we running these machines, or are these machines beginning to run us? Right? The whole fabric of society is coming apart. Look, see, America is so polarized. Why are they so polarized? It's a confirmation bias. These AI engines have figured out what you want to hear, and they're feeding you that. So it means that how will you possibly change your opinion when it is pandering to your pandering to your prejudices rather than actually informing you. Today, it is almost impossible to get objective news on the internet, because the moment you open the computer, you go to any of these major sources of news, Google and so forth. All of these engines have AI driving them, and they are not, the AI is not interested in giving you objective news. It is interested in pandering to your prejudices. And it is just sitting in the so-called recommendation engine or the preferences engine. All they do is they pretty much are figuring out your bent of mind. Now, it is all, you can say that it's all very innocent. It is very useful. It's giving you what you really want. But do we really want what we do? Is that a good thing? You know, in Chinese, there is a very interesting curse. The way the curse goes is, may you live in interesting times.
Oh, that's actually fake. Someone made it up. We don't have it. That's actually fake.
It's actually okay.
It's actually fake.
But nonetheless, it is interesting. So apparently the saying is, may you live in interesting times and may all your wishes come true. Right? And it's supposed to be a curse. And I don't know who cooked it up. But thank you, Dennis, by the way, for correcting me. For many years, I believed it was a Chinese saying. But it is true. These machines, the curse of these machines is that they're pandering to our wishes. And that is the terrible thing. None of us are getting news. None of us are getting facts. What we are getting are all this concocted content that is literally, you see, guys, that the fabric of society is being torn apart. 70 million people don't believe in the face of evidence that this election was fair. Right?
Many of us do.
Go ahead, Kate. Kate, you said something. No, you're on mute. Okay. So this is it, guys. You know, what is it? What will we start believing in next? There are websites devoted to alien landings. There are websites devoted to, I remember once from India, somebody with great gushing sent news that in some sacred temple or mosque or whatever it was, they discovered.
You said something. I'm sorry, I'm stuck behind because I have to use the YouTube link. So I'm always behind.
I apologize. So yeah, in India, somebody sent me a gushing news, which was just the buzzword. And I received the same news from many sources. Apparently, they had gone down to the labyrinths or basements of some great, I don't know, some great church, temple, mosque, I forget what, some ancient one. And then they found, when they opened something, they found a treasure. And when they removed the stone, in the complete darkness of the basement, apparently there was so much jewelry that it glowed so much that the whole room was lit, and these guys were practically dazzled to the point of blindness. So sounds very sensational, right? But if you really think about it, common sense physics, none of the jewels are self-luminescent. Diamond, if you put it in a dark room, is still dark. It doesn't have self-luminosity of its own. Right? It is not like radium or something like that that's radioactive. It is emitting out light or glow. Right? These are inert material. And yet something that runs across the world and becomes a big sensation, it just takes you 5 minutes of scientific thinking to realize, not even 5 minutes, to realize that this is rubbish. Right? So that's the fear of AI, because how are these news propagating? In the old days, they would go by letter. It used to be a nuisance. But now the AI engines are catalysts to it. They figure out, they know that you will salivate to hear this. And therefore, they feed you this fake news. So these are not just, passive conduits or highways of knowledge. These are very active deciders of what you do and do not get. And they feed you rubbish because you're gullible enough to eat rubbish. This is true for all of us. It's true for me. All the time I keep asking myself, in what area am I gullible?
See, going back to the fundamental question that Patrick posed, right? Now, like I'm going back to my MBA days when I was doing some little, principal component analysis, like factor analysis to figure out things. There, the concept was when you get those weights, you try to interpret what the combination of weights mean.
Yes.
And you try to relate it to your business context and try to get some implicit connection. To that extent, it is explainable. Right? I would assume right now, things have become so complicated in terms of those underlying matrices, it is impossible to associate it with anything that you can realistically map to.
See, Premjit, that is the popular belief that these things are black boxes. But the truth is, there's an enormous amount of research and energy being devoted to interpretable AI and explainable AI. And in fact, in the workshop that just preceded last year, that we finished in January this year, in a boot camp, and some of you were there in that boot camp. Praveen, you were there. Anil, you were there, and Kate, you were there. Shini, you two were there, and I don't know who else was there. And Shankar, I don't know if you were. Shankar wasn't there. So anyway, we devoted an entire day to interpretability of machine learning algorithms. So how do you bring back interpretability to black boxes? So the technology is evolving. The theory is evolving. It is not the way the popular media makes it out. You can take a black box and superimpose an interpretation to it very coherently. You can make locally, reliable approximations of these models in specific areas and so forth. And so there's a lot of work that is being done. It's a growing area of research. I would never just throw in the towel and say they are black boxes. I would seriously look at the research that has been done and techniques that have been developed, and they are available. It is all Python code. Those libraries are available. Just use it, impose interpretation on top of it, and it is as far as we can go. And those interpretations are pretty good.
And is it applicable even for NLP contexts?
Every context.
Okay.
Right. So it is there. See, the theory is fast evolving. Right, the field is, I wouldn't say here, the field is fast evolving because it's the need of the hour. The fact that these models are not interpretable is a very, very serious threat to society at this moment.
Right, thank you.
Asif, on a side note, how important would you say convex optimization is for the general subject of AI?
You see, it's very interesting, convex optimization. See, there is linear optimization is straightforward. You always solve it, right? More or less.
Mm-hmm.
The moment you go to quadratic and higher problems, the people nonlinear problems, there's always a situation, can it be solved? People believed, and we know it for a fact, that if you can reduce a problem to a convex optimization problem, then it is solvable. Right? So Boyd used to teach at Stanford, the convex optimization. He probably still does. His book is excellent, by the way. So should we learn it? I would say that just for the sheer beauty of the subject, you should do it. I believe, Shankar, you have taken his course, Boyd's convex optimization, isn't it?
Yeah. But I think for a job point of view may not be.
Oh yeah, it is not at all useful. It's beautiful. See, this is, I suppose it's its own uncertainty principle. Things that are absolutely sublime and beautiful have very little practical job value. Having said that, I would also say that AI, deep neural networks, inherently is a non-convex problem. So people in deep learning, so there was a belief that in machine learning, you have to reduce every problem to a convex problem. We now know that is not true. It is true that every convex problem can be solved, but it is not necessary that if a problem is not convex, it cannot be solved, right? So people in deep learning literature, they refer to those old timers as people suffering from convexivitis. So for example, deep neural network, completely non-convex loss functions. Right, lots of hills and valleys. We did that. Remember the loss function visualizations.
Yes.
So deep learning is effectiveness of deep learning is a standing proof that you have solutions for all sorts of loss functions, not just for convex loss functions.
Mm-hmm. It seems like something I might read up on just for the fun of it.
But do that. The Boyd's book is available freely as a PDF. It's an excellent book, very readable. Even if you read half the book, it is worth learning it once in your lifetime. And you'll have to give maybe, I don't know, a month to do that.
Can you spell his name? Boyd.
look up this book.
Right.
It's not here in front of me, otherwise I would have shown you.
Okay, thank you.
Anything else, guys? All right.
One
then
question.
Go.
So when we use BERT for some fine tuning, like classification, I think you're going to cover next week, possibly. So this for example, you showed one sample that cow jumped over the moon. That could be multiple sentences for which we could try to classify. Then what happens? And you insert this separator at the end of each sentence, or how does it work? And then that's one question. The second question is in the BERT paper and in the BERT GitHub repository, they mention about the sequence length. Sequence length is one of the parameters. So the maximum sequence length for fine tuning is about 512 or something for the base model. So can you please elaborate on it? Probably if not today, probably next week.
It's a very good question that you raised. Actually, let me answer the first one, which everybody will understand. And the second one I'll speak, but people can feel free to drop off because it gets technical. See, the first part is simple. The definition of sentence, if you read the BERT paper somewhere up there in the beginning, it says that the definition of sentence in NLP, in deep learning, is not the linguistic definition of sentence. See, when you come to a full stop, you say that your sentence is over, isn't it? But in this literature, a sentence is arbitrary thing. You define it. Could be a paragraph. It is one sequence that you feed in. Right? Is a paragraph is a perfectly good sentence in as far as these transformers are concerned. Right. So it is your logical definition. What is a sentence? Or it could be half a sentence. For example, the clauses of a sentence could be your sequence, or one would be your machine learning definition of a sentence. So that is one. So for example, when you do this sentiment analysis or classification, yes, it's perfectly reasonable to feed it the paragraph and expect an output. And now comes the next part. What happens when the sequence length exceeds 512? So there is literally, I mean, people have studied that quite a bit. Look into long formers. Long formers are transformers specifically that transcend this limitation. And I would love to cover long formers on one of the weekends if enough people are interested on the Sunday reading.
Yeah, thank you, Asif. Another thing I was surprised was the length of the vocabulary in BERT, the base BERT. It's about at the most 30,000. And it uses this tokenization called word piece tokenization. It puts stars into. How does that work so well compared to basically the other things that have multiple millions of words?
Yes. See, what happened is there's something surprising actually came out. The word pieces paper, this is a paper in itself, right? So let's take some esoteric word. Right? I keep using this word. What is it? Heteroscedasticity. Right? You would imagine that this is a fairly infrequent word, isn't it? It's it would be rarely seen in much of human literature, but it does occur. But if you look at its constituent parts, hetero, right? Skedastic, right? And city and all of these pieces, those are much more common, right? So it is built out of common building blocks. It's just an unusual combination of relatively common building blocks. So the question that was asked, and so the word piece paper, by the way, there is more to it. And the why you do word pieces or how you do it is the reasoning starts with character level. So you just start with the most common occurring character, then you append another thing, then so there's a process of accreting or growing it in a synthetic way, but we'll leave that aside. The gist of it all is that if you create a vocabulary not of words, but word pieces, you will need a smaller vocabulary and a much more meaningful vocabulary. Because if you really think about it, the word hetero, whatever you prefix, hetero word piece itself has a meaning, isn't it? It represents some level of variety or non-homogeneity, right? And so that meaning can be, the semantics can be applied to a whole set of words as a prefix. Shankar, are we getting that?
Thank you.
Yeah, so that is where the word piece paper comes in. And generally, now we know, I mean, this is one of those little things, we don't talk about when we do sample code, etc. It doesn't get to, but I did, I don't know if you were there in this session, but I did emphasize that in word embeddings, right, that the state of the art now is word pieces. Given a choice, always use word pieces, not words, right? That's a basic thing.
Thank you, Asif. Today's class was great.
Yeah.
What are you going to cover next week, lab?
Now we'll do some. We will actually train about. See the transformer lab that we did. Actually, you didn't do, right? You didn't do part 1, did you?
I went over it's on the website, so I went over it. Used the Hugging Face Distilbert.
That is right. So if you look at that, we used the freebies, right? We used the Hugging Face API to solve a variety of problems. We did not actually train a transformer, right? Or fine tune a transformer. In the coming weeks, we will fine tune a few transformers. So
that would be great. Yes, that would be great. Thank you. Thank you.
Yes. Actually, stay back, Shankar. I wanted to talk to you for a moment. All right, guys. Good night then.
Thank you, Asif. Good night.
Yes, Asif.
All right, take care. Good night.
Thank you, Asif.
Good night, Asif.
Good night.
Yes, good night.
Thank you.
You're welcome, Kate. By the way, Kate, was that fine what we gave? No, she's dropped off. Who else is there? Arithya, are you? Yeah, there are 2 of Arithya here. I think you logged in from 2 machines and you forgot to log out of one. So, Shankar, I just wanted your feedback as we are going through this workshop. How do you like it so far?
I think today's class was wonderful, and for me, at least for me, the Spacey was really useful. I really got to use parts of Spacey that I have not used in the past.
Yeah.
So that was, I went through the book that I saw that book a couple of years ago, probably a year ago. But then this book, I got a chance. Without the class, probably I would not have gone through the book. Yeah, you strongly recommended it, so I just followed it through.
See, in simple terms, there's no reason to use NLTK.
Yeah.
If Spacey can do it, because it's much faster, more production grade. But most of the textbooks in this field are written using NLTK.
Yeah, there are challenging problems there. Again, everywhere, all these models, the labeling is a very crucial piece. That's where most of the companies don't have, and then they expect, they have the resources, they expect something great.
Yes.
So that's a challenge. So today's class was, so these 2, I think I'm looking forward to the classes, probably today's class and the next 2 weeks. That will be very useful for me.
Okay, very good. So the autoencoder, you didn't find that useful because you probably knew that already.
Yeah. But I think Spacey was, I was surprised. You put some good effort on it, and then I followed through it. I think that the main thing was you didn't have time. You had to cover other stuff. But I think you gave a very good starting stuff for Spacey. And then from there, and then you gave a good reference book also. I think that was very useful for me.
Yeah.
At least in my work
Oh, nice.
I put it into use.
Good, you got something out of it. See, Shankar, each of these topics that I'm introducing any given week, right? Ultimately, to the extent that I have to time box this course.
Yeah.
I have to keep moving fast. But I put all those references on the class portal.
Yeah.
I really keep wishing that people, you notice that those references are not just random picks. I very thoughtfully put them there. If only people followed it up and read it, and it would take them far. It's just that I think this course has gone, they're tired by now, or the holiday season has kicked in.
Yeah, I am very sure that the next 2 weeks will be very super useful for me.
Oh, nice. And by the way, this transformer explanation, what did you think of it?
It was good. I went through some of those in the past. Today, I think I came to know a lot of other things. I went through this McCormack's YouTube videos that you put on your website also.
That's right.
Yeah. So I went through. He's giving he gave a good explanation, layman. But I think yours is more more in depth, going into those matrices like how this Q, KQ, and some of the details I didn't know. So that was useful. How would the K and Q go into the
That's right.
decoder, and then
do you
from
even
there.
have these three vectors, right?
Yeah.
The basic question, why do we have three vectors? Surprisingly, three vectors come out. One word goes in, three vectors come out. Why?
Yeah. So I worked in a couple of companies. So it's a challenge to get this GPU machines anywhere. So I worked at ServiceNow. ServiceNow is like a pretty rich company.
Yeah.
I tried almost like for a year. Not only me, I was just a small contractor there. Even in the machine learning group, they didn't have access to GPU. But on the other hand, Apple's, Google, and Facebook, they use left and right. They have so much resources and so much. Anybody can put in spin a virtual machine. So that's the challenging part here.
Right. See, Shankar, I have taken a stand like this. Right from the beginning, I used to build my own hardware, even to do the day job. So what would happen is I used to be very productive. I mean, for in things, I would never get blocked on. I had a basic principle that when you are thinking, when you're coding, you are in a zone, and nothing should take you out of that zone, right? Distract you and so forth. Hardware, just get the hardware. At the end of the day, it works out because what happens is you keep moving forward, right? You don't get blocked on hardware or something. And ultimately, whoever is paying you ends up compensating for it. At some day, you just say that I have spent 30,000 on this hardware this year. You better make it up, and they'll immediately make it up or something like that. See, ultimately, when the results come out and they're impressed or they're happy, then the checkbooks open. The problem with corporate world always is when you ask for things to do and the results are not there, they all drag their feet because they don't see something. But once they see something and you say that the next result is not likely unless I have this, and then the argument becomes more powerful. But it is an unusual thing I did all my life. I just made sure that I use my own hardware. I would never use the corporate hardware. They're rubbish anyway.
So are you going to probably extend the transformer lab you did for the first workshop, or are you going to do something different this time?
No. Next 2 weeks is transformer labs.
No. I saw one notebook on Hugging Face.
That is elementary. No? That was for
elementary. Yeah.
That was
so you are saying that you are going to even train a transformer.
That's the point. We'll train a transformer, a few transformers for a variety of tasks. Yeah. That is the fun of it, no? Because in practice, that's what you'll do.
Yeah, exactly. Yeah, that will be like a real powerful tool for anybody working in the industry.
Yeah, nice, Shankar. It's nice to talk to you, to hear your voice. Yeah,
Thank you, Asif. Thank you.
Nice. All right then. Yeah, good night.